In the previous units, we've looked at vector combinations by addition and subtraction. In this one, we're going to consider a few ways of doing multiplication. And in particular, we're going to encounter the challenge here that there are different ways to multiply vectors. And the two we're going to consider are scalar multiplication and the dot product. And explicitly, we are not going to look at the issue of cross product. So in fact, there's three common ways to do multiplication with vectors. These are two, cross product is a third, and we're going to focus on these first two here. Scalar multiplication is the simpler of these two, and that just means multiplying a vector by some scalar or a single value, a real number. And that would be something like 2 times the vector 3, 7 or something. That is going to produce a new vector. So inputs and outputs are important here. It's not just numbers lead to numbers. A scalar times a vector will give us a new vector. The idea of this is what you might expect when you multiply something by, say, 2, is that we're going to get something that's 2 times the original vector in length, and it's going to be the same direction. Up to a little asterisk here. If we multiply by a positive number, like 2 times a vector or 4 times a vector, then we just change the length, or we could also multiply by a half. All of these will point in the same direction as the original vector, but if we multiply by a negative number, like negative 2v or negative 1/3 v, then we're going to get something that points in the diametrically opposed direction, but also has the scaling effect, shrinking the length or doubling the length. Just to illustrate that graphically, if we had a vector like this, let's call that v. If we take 2 times v, well, let's draw v here in perspective, and we imagine this is the length here, then we're going to get twice that length, but the same direction is going to be 2v. So if we scale it, literally scale it with a scalar multiplier, scale it by 2, we're going to get twice the length, but in exactly the same direction. Let's do the one down here, negative 1.5v first. Again, here's our length. Let's put the vector roughly in the same place. The negative reverses the direction, and the 1.5 is about the length scaling. So what we're going to get is a vector pointing in the opposite direction. There's one full unit. There's another where a unit is the length of the original vector v. And we're scaling this out. There would be our 2 times the length of vector v out to here. This would be 1.5 v to there. Let's try to make this a little prettier with a straight line. There we go. So half again is long and pointed in the opposite direction. Last but not least, if we have the vector v again, and we multiply it by 0, which is obviously a special scalar, we're going to get the 0 vector. And that's that special vector that has no direction specified, and it doesn't need a direction because its length is 0. So it's that one vector out of all the vectors where the direction is not really defined. The nice thing about scalar multiplication is that its component version, when we do multiplication in components, is very, very straightforward, and it actually matches our intuition very closely. If we have the vector 5, negative 2, so that would be 5 across and down 2, that would be our vector v here. If we take 2 times v, well, mathematically, in notation, this would be 2 times 5, negative 2. All we do to evaluate this, or one of the options for evaluating it, is to multiply this 2 into each component separately. And so we'd end up with 10 and negative 4. And that's it. 0 works exactly the same way. This time we don't have to worry about the meaning of the 0. We just take that 0 and multiply it in, and we explicitly get the 0 vector after that operation because both components end up being 0 after we multiply out. And last but not least, if we take negative 1.5 we're going to get negative 7.5 and positive 3. And just for comparison here, this would be left or negative x direction by 7.5, up 3. This would be our vector negative 1.5v, and we can again see that pattern graphically. This vector was v to start with. Multiplying by the negative, when we look at it in components, automatically takes care of the change of direction, and we see the scaling that it's 50% more travel in both the x and the y directions. So that's the way we can look at the component version and the graphical version together of scalar multiplication. Now, most of the other operations that we'd expect with multiplication by scalars apply here. Most of these are ones that we've seen before in terms of addition, but we've added a couple terms here. Distributivity. Let's do a quick example here. If we had two numbers in parentheses times a vector, well, we could take 2 times the vector and then 3 times the vector, or 2v and 3v, and guess what? We'd get 5v, which is what this side here would equal. And this law basically captures our intuition that whether we simplify what's in the brackets first, or whether we had two separate things that we could group the scalar multiples, we can do all the things we'd expect to do with multiplication like we usually see it done with regular scalars. The fact there's a vector on the end doesn't change anything. Multiplying by 0 scalar gives us the 0 vector. Adding the 0 vector doesn't change anything. Again, the same basic rules we see with real numbers. The only thing that's really interesting here is this idea of multiplying by -1 is the way we can transform a vector to get one of the same magnitude, but which has the opposite direction. So if we want to take a vector and turn it around 180 degrees, then we just multiply it by -1. That would reverse the x component, reverse the y component, and give us a vector pointing in the exact opposite direction. We'll be using this kind of vector from time to time as we go through the rest of the course.